Hi there. This video will learn about the superposition method for calculating beam deflections. So we have here this example, beam ABC, and it's loaded by two equal loads P at L/2 distance and L distance from the fixed support A. And we need to calculate the deflection of the beam at point C, what we call here nu C. Some textbooks call it delta C, YC, but we'll use the notation here of nu C. And to be able to calculate nu C, we can do the integration, double integration of the moment equation, and that's something we learned in a previous video. But in some cases, it's actually, there's another easier way, which is the superposition way. So this beam, I can analyze it, and also I can calculate nu C as the addition of two deflections here. So I can analyze this beam as aggregation of two beams. Like we learned in superposition when we analyzed the axially loaded members. So it's the same process. You just split the loads between two copies of the system, and if you analyze each load case by itself and then add the resultant of this load case, either it's stresses, reactions, or deflections or deformations, you will end up with the original deflection and deformation, or the aggregate deflection and deformations. So if I analyze now nu C, now I have nu C1 and nu C2 for the two load cases. If I add them together, that will bring me to the original nu C. Now, there is no point if I will have to use the integration method to figure out the deflections for both of them. It just, now I kind of doubled the effort. But the idea here is that these deflections and these beam load cases are typical, and as engineers in practice, we see them a lot in design problems. So someone did, or authors and people who kind of figure out, why not have that as a set of tables that whenever I see this load case, I will just go to the table, pull up the data and information of deflection that was calculated and used and presented in the form of a table. So this is like every textbook in strength of materials or mechanics of materials will have their own set of tables, a different way of presenting the deflections, but they're always present the lost outcome the same. So this is one format I'm showing here, and they typically show like the load case. So the first column here shows you the beam, how it looks like, what type of load is applied, where it is applied, what notations are used to represent the distances, because everything is parametric in some way. So everything is variable here and given in notation base. The second column gives you the slope, the maximum slope that happens in the beam, and the third column gives you the maximum deflection that happens in the beam and the value for it. And in the first column, it shows you where this maximum deflection happens. So for cantilever beam, of course, it makes sense that the maximum deflection will happen at the tip of the beam. And then the last fourth column here is the elastic curve of this beam. And it gives you as a reference, but what happens is mostly these tables are used for the first three columns. So you look at the first column, see, compare it and match it to the load case that you have in the design problem. And then the second and the third will give you the maximum slope and deflection, and typically we are interested into the maximum deflection. In our case here, the point of interest, point C, is where the maximum deflection happens. So we will basically match every maximum deflection for every load case with the nu C1, nu C2 that we have. So the upper beam here, where the cantilever is loaded at the tip or at the end, so that matches with our second load case. So that's nu C2 in this case is equal to nu max. and then nu C1 is equal to the other load case. So when I now go back to my problem and add up these two deflections, that will give me the original deflection that I was looking for. And the negative value here, these negative signs, means that the deflection goes downward. So negative, the beam or that point goes downward, the beam deflects downward. But positive sign means the beam deflects upward. And mostly, like, beams deflect downward because they carry transverse load pushing down. So in this case, I summarize that this is the deflection here. It's 7PL cubed divided by 16EI. Of course, one thing we have to remember here. Superposition, there is a very big requirement and kind of prerequisite to apply it. First, that these loads will result in stresses that will not exceed the elastic limit of the material. So I will be within the elastic region, and I will be able to add up these load cases and their resulting stresses and deformations and reactions in a linear way. So remember always that there's always an assumption here and prerequisite to apply superposition is that these loads collectively don't result in plastic behavior for the material. So just remember that always in engineering practice there's some kind of assumption that's used to simplify the process of calculation and analysis. So be aware of these assumptions and make sure that you are satisfying them when you use different methods of analysis and mechanics of materials. Thanks for watching, and I will see you in other videos. Take care of yourself and those around you.